Okay, so I'm going to be talking about this system here, and maybe various T-dual systems, a D3 and a D3 prime intersecting in 1+1 dimensions, and more specifically about the low energy field theory on this system. And this seems, actually, first of all, I should say this is work in collaboration with Eric Minton, who is sitting back there, and will answer all your questions, and with a former graduate fellow, Sichin Sun. So this seems like a pretty cut and dried thing. One has a U1 multiplet on this D3, a U1 multiplet on this D3, and some kind of charged hypermultiplets moving on the intersection. But as you'll see, there were 4 or 5 unexpected features that we ran into in trying to understand this low energy effective field theory. This began long ago by thinking about top-down models of ADS condensed matter, where you're trying to engineer specific quantum field theories. But this, what I'll say, has probably nothing to do with condensed matter physics. It's just an exercise in quantum field theory. I don't know if it's significant for anything, but as you see, it makes for a nice story. So the motivation for thinking, well, so there's a puzzle here, and to explain the puzzle, let me start by considering parallel D3-branes. And now, of course, there are BPS states, which are stretched F strings or stretched D strings. And the F strings are electric charges under the D3 brane gauge groups, and the D string is a magnetic charge under the gauge group. And now if we take the separation to be very small, both of these states will become arbitrarily light compared to the string scale, and so we should be able to describe them in an effective field theory. And of course, we know how this works. The F strings become the W bosons of U2, the gauge group. And the D string becomes a soliton in the same gauge theory. It becomes a magnetic monopole. Okay. Now there's another logical possibility that didn't happen, but it's worth mentioning it, which is that it could have been that as we took the separation small and looked at the low energy effective field theory, it might have been that there were actually independent fundamental magnetically charged degrees of freedom. Now, in this case, that would not be sensible because it would imply large non-perturbative effects. Since these have couplings of order 1 over G, it would imply large non-perturbative effects at low energy, and this system is perfectly perturbative. Of course, there are cases where you do get various wrapped D objects becoming fundamental fields in the effective field theory, like the conifold. The Strominger showed. Arkady?
Yeah, but I wonder that when you're doing this limit, you are getting this effective theory is it in weak coupling? Or, I mean, because of course you can get electric description, implying the W and solitons are heavy, or you are getting other way.
Good. So this system, let me suppose it's weakly coupled, so these are lighter than these. But of course, we know that this whole system inherits an S duality from the string theory, and so whatever effective theory you get should have an S duality within it. Okay, so as Strominger showed, if you in the conifold, when you take wrap D objects become arbitrarily light, but they become fundamental fields in the low energy effective field theory, and that's okay. Large non-perturbative corrections are possible because the conifold is a singular. From the point of view of the string world sheet conformal field theory, the conifold is singular, and so perturbation theory can break down. Here, of course, for just D3-branes, there's the conformal field theory is perfectly non-singular. So this is all familiar. But now let's apply the same reasoning to the case here. So again, this system has, let's suppose they're separated in some other transverse direction that I can't draw. This system has F strings stretched between the 2 branes. and it has D strings stretched between the two branes, which are electromagnetic sources. And now the same question, as we take the separation very small, so these F and D strings become very light. So again, the F string just becomes the charge field moving on the intersection. How does the D string appear in the low energy effective field theory?
So take the separation to be small in 2, 8, 9?
Let's say the separation to be small in the 8 direction, right? Or the 2 direction. And separation small in, right. Separation small in those transverse directions. Right. So we take the separation small in these directions, the stretch strings, they're still BPS, so they don't disappear from the spectrum or do anything funny. They become light, and so they should be represented in the effective field theory. And now the question is, how does the magnetic object appear there? Again, one possibility would be an independent magnetically charged field on the intersection, but again, that can't happen for the same reasoning as here. So somehow it seems that this D string has to be represented in the effect, has to be some kind of solitonic object in the effective field theory. But the effective field theory now seems too simple to support such a solitonic object. You have simply abelian gauge fields on each brane, and then you have charged fields, electrically charged fields, the F strings moving on the intersection, and how do you build a magnetic monopole out of those ingredients?
I wonder, does that, because one of possible kind of suggestion could be that this intersection itself is soliton. You see, imagine that you have like a stringy soliton, and you can have different types of them. And then I can see these charges as a kind of that when you have different strings, right? Then when they meet, at this point you can have either magnetic or electric charge.
Okay, I don't want to think about this. I mean, I want to think about the picture we get from string theory. There's not some extra degrees of freedom to make the brane solitonic. We just have the low energy limit from string theory seems to just contain again abelian gauge theory. I want to confine our attention to this field theory: abelian field theory here, abelian field theory here, hypermultiple moving on the intersection, and somehow that system has to have within it. Seemingly, but either there's some gap in the logic somewhere else, or this system has to have within it a magnetically charged soliton.
John, do you want to describe it as a soliton in 2 dimensions?
Well, it has to live. It has to have a magnetically charged object, and the only place there's any interactions are on the intersection. So it has to somehow be a 1+1 dimensional. I mean, it has to live at the intersection, and this 1+1 dimensional field theory. Well, this is a hybrid field theory, of course. There's interactions between the higher dimensional and lower dimensional fields. But it will live on the intersection, but somehow be a magnetic source for fields that stick out into the D3s. So the first thing is to write down the low energy Lagrangian for this system carefully. Actually, good. So Jaume asked why I didn't use the 2 and 3 directions. I'll use them now. One wants to make use of supersymmetry. So this configuration has 8 supersymmetries. And so the most efficient way, at least for me, is to preserve manifestly a D equals 4, N equals 1, and then impose the R symmetry to get the full N equals 2. But of course, so there's an N equals 1 on this D3, and there's an N equals 1 on this D3, but neither of those are supersymmetries of the full system. They're different N equal 1s. So to find the N equals 1, the simplest way to think about it is to T-dual the system. So we'll fill in these two. Now we have a common 4 dimensions. And so we're going to use the D equals 4, N equals 1. We're going to use D equals 4, N equals 1 superfields in these dimensions. Now, to describe the action, say, for the fields that live on the D3, we're describing the fields of a 6-dimensional theory in terms of 4-dimensional superfields. And I don't know how well this is known, but it's a really pretty trick. due to Marcus Zagnati and Siegel.
Why don't you call the token defined prime?
I could have said, and various T-dual configuration. Yes. Although, well, yeah. Only, I'd have to, good. So once we write the Lagrangian for this, we get back to the original D3. Would you have been more likely to attend if I had said D5? You're here, so I guess it... That's right. Sorry. Okay. Anyway. Right. So there's this nice trick due to these folks, which was rediscovered by Arkani Hamid et al. And they worked out into more details. In fact, I think this presentation is the nice one to follow. And actually, it was applied to this system by Erdmenger and her collaborators, Constable, Gerard, and Kirsch. But they didn't go far enough to sort of get to where we need to get to. So I think actually of these three references, the one which is sort of most pertinent and is the most useful is that one. Although they actually did raise the puzzle of how is S. They asked the question, how is S duality realized in the system? By the way, of course, you might say, what about holographic representations? If instead of one D3 I had n D3s, then there's some version of the system which is a probe D3 prime in an ADS5, and that's interesting too. And the holographic pictures were discussed by, again, Constable et al. And by Rychkov and Witten. But I want to sort of ask about the Lagrange, the field theory version. What is the field theory that holographic system is solving? So okay, so we're going to proceed with this. Actually, so we're interested in describing a 6-dimensional system in 4-dimensional superfields. But it's simplest actually just to go all the way to 10 dimensions and then drop down, or at least most elegant. So everyone knows how you write n equals 1, d equals 4. Anyone knows how to write n equals 1, d equals 4 in terms of n equals 1, d equals 4. You have a vector multiplet, and you have 3 chiral multiplets. And let me use x for 0, 1, 2, 3, and y for 0. Sorry, I've already said I'm going to use for the directions 4 through 9, the directions that are not in these 4. I'm eventually going to group them into complex pairs. So z and z bar for the other 6. So to do this, you simply have 1 vector multiplet and 3 chiral multiplets. But now this, of course, is the dimensional reduction from n equals 1, d equals 10. And similarly, this familiar description can be obtained by a dimensional reduction as shown by these folks. So the first thing is, of course, these fields now become functions of the additional 6 dimensions. But these extra 6 dimensions have nothing to do with the supersymmetry. You should think of them as parameters. So you should think of having an infinite number of 4-dimensional superfields parameterized by the z's and z bars. And there's the gauge invariance, which acts in the usual way on the vector superfield, where lambda, though, is again now a function of the parameters as well as the coordinates. But the chiral fields have a more complicated transformation, which you can expect because the chiral fields, after all, become the gauge fields in these extra 6 directions, in the z directions. And so they should transform like a gauge field. And so phi sub I goes to e to the lambda. So I'm writing these, by the way, for the non-abelian case, but just to be a little bit more general, but I'll eventually drop down to the abelian case that I need. Okay, so the chiral fields transform in the way you would expect chiral fields to transform, except now because they're gauge fields, they transform like a gauge field. So you've got this extra piece. And now you can write down an action with these fields that has these gauge invariances. I want to trace somewhere. Just put it. Trace around everything. So the usual construction of the gauge field strength, and now a term which is sort of familiar and sort of not. All these conventions are taken from the Arkady-Hamed paper, if you want to pursue this. Good. Okay, so this part, there's another line, but this part you'll recognize part of, if again, from writing the n equals 4 theory in terms of n equals 1, you know that you get this cubic superpotential. But
some epsilon symbol.
and there's an epsilon. Thank you, thank you. Yes. Yeah. So from writing the n equals 4 theory in terms of n equals 1, you're familiar with this cubic superpotential. But now because of the gauge transformation of the phis, same phis, it picks up this extra derivative term. It looks sort of, I guess, Chern-Simons like.
And it is always these, right?
Sorry?
DJ.
Oh, I'm sorry. Sorry, yeah. The eyes are always. I should. Sorry. I should let me put that like that. All right. So I should do that because there's so many dimensions here. If I'm careless, it'll get confusing. Good. Okay. So there's that, and then there's also the
What's the rule for integration over these?
they're just flat 6 flat coordinates. They're just. I'm not putting in the factors of 2 here, but it's just d6 at d6. Yeah.
But when you're on the brane, you kind of have like the delta function over these or something like
that. The delta functions will come in. The delta they're not here yet. I'm just doing the d3s.
I see.
There will be delta functions later.
Mm-hmm.
Yeah. Actually, wait a second. I want to just continue inside the parenthesis. I'm going to, hopefully I will close it. There, am I closed now?
You need one more in the previous.
Okay.
At the end.
Okay. I probably need another one here.
Plus a
Hermitian conjugate. What a great audience. Thank you. Good. Okay, anyway, in line 2, you'll recognize, if you ignore the z derivatives, you'll recognize just phi I bar phi I, the usual kinetic term for the hypermultiplets. And again, because of this gauge invariance, it needs to be completed in this particular way by derivative terms. And actually, there's also needed a Wess-Zumino-Witten term, which I won't mention because it drops out in Wess-Zumino gauge. It also drops out in the abelian case. And so, okay, so this is very pretty. I think this is very pretty. Again, if you only know n equals 1, d equals 4 superfields, and you want to, which is all I know, and you want to write down the n equals 1, d equals 10 theory, this is it. And in the abelian case, this second line so in the abelian case, the second line simplifies quite well. It looks nicer. We're going to
But
need
you've got an infinite number of four-dimensional fields?
infinite number of four-dimensional fields, yes.
I mean, do I expand in powers of Z or plane waves of Z?
No, you don't have to. I mean, we don't. Well, you might do this for perturbation theory, but no. Right now, it just taken on its own terms, I think. Okay, and so in the abelian case, the second line simplifies. Okay, so now for our system, we are going to dimensionally reduce on well, for the D3, we're going to dimensionally reduce on Z2 and Z3. For the D3 prime, we're going to dimensionally reduce on Z1 and Z3, and so you can ignore some of these things. Also, the non-abelian terms, since we only have one of each, D3 won't enter. And then we'll still have to write down the third part of the action for the intersection fields. But actually, before I go on, let me give you the names of some fields, because again, there's a lot to keep track of. So over here we have on the D3 again and the D3 prime, we have a vector multiplet and another vector multiplet, and I'm going to call these, just to give them different names, Q1, Q2, Q3, and S1, S2, S3. But again, I want to keep track of the dimensional reductions here. So these two components start life as gauge fields, but when we go back to the D3 system, they become scalars, and they're SO4 partners of these. So let me actually indicate that. So these and these become in the system of interest scalars with an SO4 symmetry, and correspondingly, these and these, or these and these become the gauge fields on the branes, right? So everything which is tangent to the brane.
But in 1+1, you do not have a kind of physical gauge field, right?
Right,
So,
but that's right, we don't. But this action is right. But we're talking about the D3s, so we have physical gauge fields on the D3s. So right. Good. So the reason. So now I want to come to the sort of first important part of all of this. I want to pick out from this action the terms that involve the auxiliary field of the vector multiplied of D3. And let's see. So let's see. They come in two places. Well, first of all, there's the usual 1/2 d squared. There is the so hiding in here we have d times the lowest component here, and there's a z derivative, and vice versa. So there's like plus d times partial I partial zi q bar j plus partial zj q bar I. And actually, I forgot, I still got to write down the hypermultiplet action. So the hypermultiplet fields, there is I'll call it B, which has charge +1, -1 under the two U1s, and C, which has the opposite charges. And so we have integral d4 theta, B bar e to the v minus v prime b plus c bar e to the v prime minus vc plus integral d2 theta q3 minus s3 bc. So the first line is just the gauge numeric kinetic term plus Hermitian conjugate. And the second line is the superpotential, which has to be there because, of course, when the two branes are separated, when Q3 minus S3 is non-zero, this gives mass to the hypermultiplets. Okay, And so I wanted to pick out what the D term couples to. Of course, it also couples to the hypermultiplets. Let me put in the integral over the D3 brane. But now the coupling to hypermultiplets has this this delta function that Arkady mentioned, since the hypermultiplets live only on the D3 brane, and then what is B bar B minus C bar C half B bar B minus C bar C. Okay, good. So now, and I probably have to close the parenthesis again. Good.
How does that? How do the indexes work out for IMG?
Sorry, Z1 and Q1. Excuse. Thank you. Boy. Thank you. Sorry. Because the reason it's only 1 is because we've reduced in the 2 and 3 direction. There are no. For the D3 brane, we've reduced in the Z2 and Z3 direction, so only Z1 survives. Thank you for catching that. Good. And so when we integrate out the auxiliary field, we get the square of what's in those parentheses. And now remember that, again, this hypermultiple is actually going to become a gauge field on the D3 brane, and this combination is, this combination here is just partial 4 A5 minus partial 5 A4. It's just the field strength built from that gauge field. And so the action when you integrate out D contains partial 4 A5 minus partial 5 A4 plus this last thing, delta squared. Now, if you look now at the field equations for the gauge field, you want to call this entire combination, not just the curl part. You want to call this the field strength. And the reason is when you vary A, what you get is, with that definition, you get partial mu. F mu nu is just the variation of A in the hypermultiple action, is just the electric current from the hypermultiple. So that's the appropriate way to define the gauge field. But now you see that the gauge field strength is no longer a pure curl. It has this non-curl piece. And so the Bianchi identity is no longer trivial. It's J nu magnetic, where J nu magnetic is epsilon nu lambda, partial lambda. Actually, I'm going to call this combination here P. P is basically the hypermultiple contribution to the D term. P, again, times this delta function. And these mu's, this is a two-dimensional epsilon because these are tangent to the tangent to the intersection, tangent to the 0, 1 directions. Okay, so
but it looks like topologically conserved, right?
It's topologically conserved. That's right. Exactly. So in fact, hiding in this system, you have both the usual electric couplings of the intersection strings to the gauge field and the D3 branes, but there is also a magnetic coupling of the hypermultiples of this form to the D3 brane fields. And as Arkady pointed out, this is topological. So the magnetic charge density is just the spatial derivative of the hypermultiple D term times the delta function, of course, because it lives on the intersection. Good. So it seems like we've more or less solved the original puzzle. That is, we found that, in fact, there are magnetic sources on the intersection, but I have half an hour left, and I'm going to need it because things are not quite as smooth as that.
But to have it non-zero, you need to have this p changing along.
Good. So actually, before I erase it, I want to point out something I'm going to come back to later, but I'm going to probably have to erase it and rewrite it. Some of you might be bothered that when you square this out, there is a delta function squared. Since we have a source localized on the intersection, that's not going to be a problem at all. That's going to get taken care of automatically. But if you're worried about that, don't worry about delta of zeros. But okay, good. So this is the x1 direction, and the vertical direction then is this combination of the hypermultiplets. And so a kink. So this is very nice. This term transforms the natural 1 plus 1 dimensional soliton kink into a 3 plus 1 dimensional magnetic source. And so it's all very pretty, and it looks like we're done, but we're not done. The reason we're not done is let's work out the potential for P. Well, okay, so the potential, the first thing I picked out from here was the U1D terms, which again gave us our modified field strength. Again, it's funny because of the way this trick packages things. The gauge, what we think of as the gauge field kinetic terms, come in part from an unusual place. They come from the auxiliary field in the gauge multiplet. But now the potential for the hypermultiplet fields, of course, we've got this here. And so if we look at the auxiliary fields F sub B and F sub C, we've got this potential. We've got this potential. Again, P here is and so now we have a problem because the potential, we don't have the right kind of potential to produce any kind of kink soliton. It has a unique minimum at B and C equals 0. But when the branes are separated, which is the case.
But if your Q3 equals S3.
Yeah. When they're when the branes are separated, the D string has a finite mass. It's still there. But when they're separated, the potential has a unique minimum at which P is 0, and there is no such soliton. So we still have a problem.
Can I ask another?
Yes.
What quantizes the asymptotic value of P?
That's a related problem. We would have been happy if we'd found some kind of sinusoidal potential with a series of minima that would quantize it. Instead, basically this Lagrangian confines magnetic charge. If we have a localized magnetic charge, we have a finite energy per unit length, and so this Lagrangian as it stands does not have the D string in it. So what have we done wrong? Well, you've been a very active audience. Happily, you didn't jump on me at the point where I made an assumption I didn't need to make. But
so you're going to do it yourself?
Yeah. But it took us, I don't know, Eric, at least a month of sweating about this. Maybe because there's a number of things you might think about. There are actually a number of things you might think about in this system that might be. But the problem is, so I assumed when I wrote down the hypermultiple action that it was just the canonical action. And in all, as far as you know, in all previous discussions of intersecting brane systems, this has been the case. But actually, if you think about it, these B and C fields are dimensionless, at least not for the T dual case, the D5 case. But in the D3 case, these fields are dimensionless, and so just on dimensional grounds, there's no particular reason that we should have taken the canonical action, we could have taken a more general Kähler potential. And on reflecting on this problem for long enough, we realize that in fact you have to do that. This system does not have a trivial Kähler potential. We're not going to need this again. So and the way to see that is to think about the interpretation of B and C in terms of branes, namely when the hypermultiplets have vevs. When the hypermultiplets have vevs, then actually what happens, of course, is that the branes reconnect.
But if it Kähler potential would be like referring to derivative term, it still would be a problem of, say, vacuum, I mean, of the king, right? So you are saying that your K will produce something effectively to change this potential?
It's going to change this potential. Yeah, yeah. So when the hypermultiplets are off, we simply have the two branes. When they're on, the branes reconnect. And this, it's important to sort of remember this is a higher dimensional thing, so I'm going to try to emphasize the higher dimensionality of the intersection in that way. And in particular, the reconnected brane, this just has to be the holomorphic gauge invariant combination of B and C. And actually, for what it's worth, in some set of conventions and units, there has to be an alpha prime in there, and that won't matter. What's the important thing, it won't matter for anything specific, but the important thing is that this relation. So B and C have this interpretation, but now what is the interpretation of B squared minus C squared, the thing that appears in the magnetic charge, the U1D term? Well, that is also a field in the blow-up. What it is it's it's a gauge field. A sub Z1 is in some set of units. This combination that I call P over 8 pi Z1. And it's pure gauge. It's pure gauge, so it has no local effect, but once we blow up the branes, there's a non-trivial cycle. And so there's a holonomy. And so the physics is actually the physics is actually periodic under P goes to P plus I guess it's 8 pi with these units. Again, the factors of 2 are carefully done in the paper, except for one that's hidden. So from the point of view of the resolved brane system, in fact, this P has to be a periodic variable, and so the moduli space of the B's and C's has to be non-trivial.
But once you get periodicity, then you immediately have this magnetic charge.
That's right. Right. So now we want to write down what this Kähler potential is. And so it's not surprising that if you impose the SO4 symmetry so that the n equals 1 actually lifts to n equals 2, the condition is that the hypermultiplet moduli space be Ricci flat Kähler. That's all. So there's a nice set of Ricci flat Kähler metrics due to Gibbons and Hawking, or maybe Taub and Nutt. I'm not exactly sure of the history. Let me think. I think we don't really need this picture again.
I don't think Nutt is a person.
It's an acronym. No, it's an acronym. Newton is an acronym. Yes. Anyway, I'm actually confused. Anyway, but I'm confused by a more pertinent thing, which is how general this ansatz is, because I happen to remember this ansatz, but I really could not figure out how general this is. So again, it's a 4-dimensional manifold. real coordinates x, y, z theta, where the curl of A is the gradient of V, and where del squared, where V is not quite harmonic. It can have a collection of point sources. And these are real coordinates, and for the translation to sort of the complex coordinates B and C and the Kähler geometry, I'm not sure, maybe there's a better reference, but the place that I found that discusses this is Lebrun. It's a little bit messy, and I'm not going to go into it. We don't need it. Okay, so here's some large collection of Ricci-flat Kähler metrics, and it's large enough to be the ones we need. So when there is just a single source, say at the origin, then this metric is really a flat metric in disguise, and it is the metric of the original canonical system. And so now we want something which is periodic, and so it's clear we simply need sources at which are evenly spaced in some direction in the period. Okay, I'll call it n to be consistent. Okay, and so we can write down metrics which did I?
That's the Igor-Ivanov metric.
It's the Igor-Ivanov metric? I didn't know that. It's the Igor-Ivanov metric. You have to tell me. Okay. Periodic tail, no. But this sum doesn't. Okay. Well, good. This is what I couldn't find. That's why I'm giving this talk. Pardon? It's on PRL. Okay. Why didn't you send us a reference? Okay. So this is the well-known Igor-Ivanov metric. And it's exactly the metric we need. In fact, this is something I didn't know, but these x, y, and z coordinates, and I'm sure other people know it, are exactly the auxiliary fields in the system, in particular with some orientation of the n equals 1 and n equals 2. Z is just what I called P earlier with some normalization. And so to make something periodic in the D term, we simply make it periodic in Z. Okay, good. So now we seem to be done, and we still have 15 minutes to go. And we're still going to need all of them, because there are several more subtleties in this system. So let me come to the first one. So I've written down del squared V. So actually, I'm really interested in the fact that this has appeared before, because there's something which, well, I'll tell you what it is now. So naively, this says that V is the sum from n equals minus infinity to infinity 1 over the square root of x squared plus y squared plus z minus 2 pi n squared. But this sum diverges. This sum diverges. And so the best we can do is to say that V is the limit, cut it off and normalize it. And whatever minus there is 1 over pi, I think, log n.
What is this periodic reduction?
Physically?
Yeah.
It's, well, so remember, x, y, and z are reparameterization of the hypermultiplet space. So it's kind of in the direction of b squared minus c squared becoming large, with bc fixed. B and c are not good coordinates for the whole space. Z is a better, but it's in the direction, again, of keeping bc fixed, making one of them large. In fact, in terms of the original period, in the original variables, the periodicity is b goes to b times bc, and c goes to c over bc. Yeah. Plus a constant, I think. Yeah, plus a, sorry, trying to get that. plus a constant. And okay, now it's got a good limit, but it has this annoying property that because of this large negative subtraction, this v, which appears in the metric, is not positive everywhere. As x and y become large, v is like minus log of s squared plus y squared plus a constant. So actually, I'm curious, just if you could say in a few seconds, how this shows up. I mean, what this means in the context of a Guryavapa, the fact that the manifold is singular.
It's a Landau pole.
It's a Landau pole.
This is the effective theory of a hypermultiplet for any U1 gauge theory, and then a Landau pole, and that's why the metric.
That's the Landau. Okay, good.
But if your constant is large enough, you can say that it's positive.
Well, but the constant is a fixed number. The story of this negative. So good. The story of this. Oh, good. So the constant is some fixed number. So we'll say more about. Well, there's more to the story. The constant is a fixed number, there's a large enough x and y where the metric goes negative. But now remember x and y, which I'm sorry, I should have also given you this. X plus iy is bc. So large x and large y correspond to large resolution of the branes. And so it's not at all obvious why there shouldn't be a singularity here. There should not be a singularity. There should not be any physical singularity in this system when the resolution becomes large. And so this is one more thing that we'll have to deal with. Good. So it's interesting this metric appears, but this metric still is not all we need because we have to get rid of that singularity somehow in the physics. So, good. So, now...
The metric has to be hyperkähler, right? I think you said basically.
I said Kähler-Rychkov, which I guess is the same as hyperkähler for...
So, this is what happens in Seiberg-Witten theory. So the whole total space of the Seiberg-Witten theory corrects the Guryavapa metric too.
Correct. So when you say corrects it, the form becomes more complicated? Okay, that's not what happens here. Good. So what does happen here? Okay, so we're going to leave that singularity aside for the second. And if we simply try to write down the BPS equation for the soliton, it'll pretty good, but there's a problem. So let me come back to that delta of 0. So I had partial 4 A5 minus partial 5 A4 plus basically T delta squared of x4 5 squared. And if you square this out, it looks like you got a delta of 0, but that's fine. It simply means that this has to have an offsetting delta of 0, so that there's no problem. But that means that the various D3-brane fields have to have logarithmic singularities at the intersection. And now, when you write down the soliton equations, since the D3-brane fields appear in the intersection action, you get delta of zeros in the soliton equations. Now, so there's a nice interpretation here. So another way to think about where these delta of zeros, I meant log of zeros, right? So there's a log singularity here. The delta of zeros are gone. There's a log singularity here, which gives rise to log of zeros in the BPS equation. One way to think about this is you've got some, let's say, some of the hypermultiplet fields. You've got some D3 field, and then you've got the hypermultiplet fields. And so you want this propagator at some value of the longitudinal momenta, the momenta in the intersection directions, but at 0 in the transverse directions on the brane. And this is the integral d2k perp, 1 over k parallel squared plus k perp squared, and it has a log divergence in the UV. So now this is log divergence coming from a loop integration, even though it's a tree-level graph. And actually, one more reference I forgot to mention, but Goldberger and Wise pointed out about 10 years ago that this happens when you have dimension 2 brane worlds. You get these logs of zeros, and they showed that you could deal with them in the exact same way that you do with normal loop divergence, normal loop graphs. You can renormalize to get rid of these log divergences. And so in particular, there's a renormalization group equation. There's a renormalization group equation for the flow of the Lagrangian, and in particular for the flow of the Keller potential coming from purely tree-level graphs, but from tree-level graphs that involve the interaction with the higher dimensional branes. I think here this mu partial mu of the Keller potential is, the constants matter, but not for anything I'll say vague. It's just the squares of the auxiliary field, the squares of the D term minus the squares of the F term, where F curly F here is the thing that appears in this. It's not the whole, it's the part of the superpotential that multiplies the separation.
So it's not like normally it would be, say, for each flat it would be 0, right? If it would be like, say, standard sigma mode. Here, if we just had, good. So the hypermultiple moduli space is Ricci flat. Yeah,
so
yeah.
if we just had that, there'd be no anomaly. But there's an anomaly due to the coupling to the higher dimensional fields.
What's F? Sorry.
F is this thing. This thing could have been also corrected. We corrected the Keller potential, but it's not. So F is just BC. And in terms of the tau nut Gibbons Hawking potential, this is just minus 2 over pi. So in fact, the tau nut potential runs, but it runs in a very simple way. The C number in there depends on the scale. And so what happens here is that this log is actually this log. And again, I want to save the discussion. I have 5 minutes, which is just about enough time. I want to save the discussion of what this means for the very end.
But then you're redefining your V, right? Taking
Pardon?
log in.
Pardon?
Then your V will take this log into the definition of new V, right?
That's right. Whatever, depending on what scale you're looking at the physics, you see different V's. That's right. Okay, so now I have 4 things to say. The first is simple. So now we can write down the soliton equations, the conditions for the fermionic fields to be stationary, and they have the desired kink solutions. We haven't been able to solve them in closed form, but we can solve them in the weakly coupled limit, and then argue that the solution persists by continuity at higher coupling. There's a funny thing, which I'll just discuss briefly, but this is something we didn't think about, and it actually is a little bit reminiscent of what Greg was saying on Tuesday. Suppose you have a sine Gordon kink, and then another one. Well, the simple sine Gordon quantum mechanics does not have such BPS solutions. They want to repel to infinite distance. And so somehow it seems as though, and the same is true in this system. The BPS equations have singly charged solutions. They don't have doubly charged solutions. So it seems as though we haven't really gotten that far because we found the single D strings. We haven't found how to describe a configuration of 2 D strings. And David Tong, in an email, pointed out this puzzle to us and also provided the solution. This is not a BPS state. So under if we do our T-dualities again, these ones, and then we S-dual, our D1s become, let me put the D1s in there.
Wait, you had D1s all the time?
Sorry, these D1s.
Those were D1s. Oh, those D1s.
These D1s. So I want to, yeah.
But you didn't put D1s at the intersection.
No, I didn't put it at the intersection. Now I want to consider I want to consider this would-be BPS configuration. And if you T-dual in this way and then S-dual, this becomes a brane construction of the gauge theory considered by Affleck, Harvey, and Witten, which has a non-perturbative superpotential. And so this is not what David point out to us is this is not, in fact, a BPS state. So there's no puzzle. In terms of this picture, you see you have a closed circuit, closed curve that runs through the various D objects. And so there are world-sheet instantons like that generate a potential. So it's all very nice. We didn't find these, and they aren't there. Yeah. That was the first. The second comment is, so again, I've T-dualed several times back and forth doing easy T-dualities. Now, the most well-studied brane intersection is, I think, D3-D5, which is also T-dual to this. So let me do this. See now, I need to first turn these both into D4s. So I'll T-dual in the non. Well, there are several places I can T-dual. Let me T-dual in the 8 direction. And now they're both D4. Wait. No, sorry, I wanted to go down. Sorry, I did it the wrong way.
Right now,
I turned
5.
right. Now they're 5. 1, 2, 3. I want to turn them into D4s. Good. But now I want to turn 1 into a 3 and 1 into a 5. So I'm going to do a hard T-duality. I'm going to do a T-duality in one of the ND directions. That disappears and these appear. Okay, so this is this is the D3-D5 system dual that we're talking about. And now you see that the D1, so the intersection directions, the common directions are these two directions, 2 plus 1. And then there's the separation direction. But you see that this teleton we're looking for is also extended in one of the directions that one of the higher dimensional branes doesn't live in. So it no longer is an object that lives in the intersection field theory. So A, there is no longer this paradox. B, or no longer this puzzle. B, yes, the moduli space, so the interpretation of the 3 moduli is very different. Right? So we had this reconnection, and one of the 3 moduli was this periodic holonomy. In this T-dual picture, the interpretation is completely different. You have a D3 brane running through a D5 brane, and the hypermultiplets correspond to kind of splitting the 2 ends of the D3 brane. And that's just an R cubed. There's no periodicity. So for the well-studied D3-D5 intersection, the story is completely different. And in particular, the moduli space, I think, is in fact just the original flat moduli space. And so the final thing is to come back to this singularity. And so again, so if you see that if we look at long enough distance scales, meaning that mu is small enough, then this is positive. In particular, the metricon moduli space for this system would be attained by taking mu goes to 0. And then the metric is definitely positive. In fact, it's positive and infinite, which is the right answer. This is something that sometimes happens in brane systems. The moduli get frozen due to log divergences. And that's what's happening here. So the metric modulation space is fine, but there are places in the combined scale and field space where the action goes bad, where if you hold the scale fixed and look at field values at resolutions that are too large, or you hold the resolution fixed and look at scales that are too small, the physics just doesn't make sense. Yes?
Why is it a contradiction? You should switch to 4-dimensional physics by that time.
Right, exactly. So at some point you should, right, so in fact, this picture of the intersection is only valid out to a certain amount of resolution, and from that point on you have to use this is what Zohar is saying, the dBi picture of the branes. And in fact, this metric matches exactly onto the metric you get from the dBi side, and again, the periodicity comes in from string instantons. But what this means is that you cannot unlike the intersection of field theories like D3, D5, where you have a trivial scalar potential, you can't quantize this field theory as a UV complete field theory. At sufficiently large scale or sufficiently large field strength, the field theory breaks down, And you have to go over to the DBI description, and of course DBI you can't quantize as a field theory. You have to embed it in the full string theory. And so the final thing I have to say is that it seems that this was not a talk about field theory at all, because this thing can't be defined. There is no field theory that can be defined that has these properties. It actually has to be embedded in the full string theory. This field theory is a fine effective field theory in certain regions of scale and parameter space, but not everywhere.
But within this region, it's okay.
Within these regions, it's okay, but not everywhere. And in particular, in the extreme UV, mu to infinity, it's bad everywhere.
But it seems exactly like the Landau pole in this respect.
Well, that's interesting. Yeah, it's interesting. I guess you're certainly right. It must be a Landau. From that point of view, you say it's an I.
In the Landau pole, the sign
Yes.
of the coupling switches from positive to negative. That's
Good.
exactly what happens here.
Okay, so it's a Landau pole coming not from loops of. It's a Landau pole coming not from loops of anything, but from trees of the higher dimensional fields. Good. Thank you. That's a nice.
But you can say call it loop, right? Effectively, because to the extent it is quantum correction.
Well, yeah. Well, it's a.
Because it goes through the bulk, but it's still a loop.
Perhaps there is some duality frame in which the higher dimensional fields are composites of intersection fields. I mean, that might do it. Yeah. So okay. So indeed, it is basically a Landau pole. So this theory is not UV complete by itself.
So if you look at this regime and look at the subleading term.
Yeah.
When you wrote that constant,
Yes.
It contains some of the exponentials.
Yes.
And so those can be interpreted as what, worldsheet instanton?
Those, yeah. So those are things which know about the periodicity, and so they know about the gauge field, and so they're worldsheet instantons. And the one hidden factor of 2 in the paper is that we couldn't get the right periodicity from the instant action. But I think that's just that they're just that we didn't chase we didn't chase through our conventions carefully enough. Yeah. But morally this is the right thing, and up to a silly factor of 2 it's the right thing. Yeah. Okay, so that's all I have to say. The Aguri-Vapa space. I'm glad you know that.
Right. So if you take 4-dimensional Zyber-Witten theory, you put it on a circle of radius r.
Yes.
Then the leading approximation is this metric.
Good.
And if you're near a place, if you're near say a massless manifold, then you get this metric, and indeed your singularity is a Landau singularity because you have an effective U1 theory, which clearly has a Landau pole. So that's the interpretation there. But in that case, there's actually instanton corrections going like e to the minus r, where r is the circle we compactified from 4 to 3 on.
Well, there are exponential corrections here, but they fall off in the direction that we're going. I mean, they're exponential in x plus y squared, so they don't
exactly the kind of correction.
Okay, good. Yeah, they're here, so but they don't fix this problem. Well,
but they do.
You said they fixed them far enough.
In the Zyber-Witten case, they do.
In the Zyber-Witten case, they do.
In the Zyber-Witten case, if you compactify on a radius r,
Yes.
then there's a series of exponentially small corrections, like e to the minus r times x squared plus y squared.
But this correction, Greg, would be
And
non-abelian.
they smooth out the metric.
I wonder now maybe.
And so I was kind of expecting that metric to pop up, but
No.
story.
No. Maybe we didn't put this. Maybe we didn't take this far enough. Maybe in fact.
I mean, I'm sure what I'm saying is correct.
Yeah.
Zyber-Witten theory, and you have a slightly different system.
But Greg, is it
Might be, it's clearly related by duality.
is it non-abelian there when you are saying this?
Pardon?
I mean, this instanton is based on kind of a non-abelian character of Zyber-Witten, or because you
Okay,
see
the way you think about those instantons in
Yeah.
that scenario that in the setup I just said is that there are world lines of BPS instantons BPS particles going around the circle that we compactified on. And those corrections, those give you exponentially small corrections, which fix up the singularity of the Aguri-Vapa metric and make a smooth hyperkähler manifold.
Right. There's that.
Yeah.
Right. Okay, but these will not work here because the problem is at large values.
Well, for us, there's a factor of r.
R, sorry. Oh, okay. So
X and Y are fields. The square root of X squared plus Y squared is dimensions of mass, and so there should be a length scale.
Okay, I'm using, okay, so these are dimensionless.
I think it's different. Here the
All right.
is when the system becomes effectively four-dimensional rather than two-dimensional.
Yeah,
It's
yeah.
a completely different kind of divergence.
Yeah, so the UV completion is higher dimensional.
Yeah.
Sort of, yeah, it's a different UV completion.
You cannot be fixed by.
Yeah, this theory is a billion, right?
Abelian. Yeah, I mean, it's interesting to ask what's the non-abelian version of it, but we haven't done anything with that. Yeah.
You're thinking of a non-abelian theory, is that correct?
I was thinking of an abelian effective theory from spontaneous symmetry breaking of a non-abelian theory. The abelian effective theory has a Landau pole. In the actual non-abelian theory, we know there's a smooth hypercalibrate pole. So okay, so maybe it's a very different mechanism.
So if you start with the theory on the parallel D3-branes and
Yes.
just turn on the background field value to make an angle, would you be able to land on this theory?
Presumably, but that's hard because you that's a good right. You can make the angle small, and we've thought about that, but right. So the higher dimensional theory knows about small angles, and so you would see everything with the intersection fields decoupling. So presumably, the answer to your question is yes. We haven't tried to do that. Yeah. It seemed like it would be kind of a hard thing to do, but you're young and strong. At least for the first 3,000 feet.
Okay, let's